The concept of time travel has captivated readers and moviegoers for many decades now. But while people have been fascinated by the idea, no one has managed to make the notion of time travel any more of a reality than before. It seems like a dream that's just a bit too far from reach. But in an age where science continues to push the boundaries of what's possible, do we even know, in theory, what the physics of time travel might involve? Curious? Click on to discover what we know so far about the prospect of journeying through time. It might surprise you to learn that exactly how time works is still a bit of a mystery to physicists. For now, travel into the future seems possible, as we hurtle toward it each day. But when it comes to potentially meeting our great-great-great-grandparents by traveling into the past, it seems either extremely difficult or almost completely impossible. Albert Einstein was instrumental in our current understanding of time travel. His theory of relativity set out a description of space, time, mass, and gravity. For Einstein, time was relative. A key outcome of relativity is that the flow of time isn't constant. Time can speed up or slow down, depending on the circumstances. The fact that it can speed up or slow down is where the concept of time travel enters as a possibility, with real-world repercussions. Time moves faster at speed, but for the effect to be noticeable, you would have to travel at the speed of light. Likewise, time passes more slowly in an intense gravitational field, for example in a black hole. The Earth's gravitational pull is stronger at your feet, so your feet are actually aging at a slower rate than your head. For us, day to day, the relativistic effects of time are too subtle to notice. But they actually do affect the satellites used for Global Positioning System, GPS. The clocks in the sky click faster than the clocks on Earth. Because of this, the ones in the sky must be constantly readjusted to ensure accuracy. If not, your map app could be inaccurate by about 6 miles, 10 kilometers per day. Relativity means it's possible to travel into the future. Whether traveling at the speed of light or spending time in an intense gravitational field, you would experience a relatively short amount of subjective time. In contrast, in the rest of the universe, decades or centuries would pass by. So when you return, you would be further into the future than the time you experienced. Relativity does open some doors for backwards time travel, but right now these haven't evolved past the theoretical stage. One 1949 study published by Kurt Gödel proposed a closed time-like curve, a path where space and time loops back on itself, could make past time travel possible. However, a major problem with this theory is that there is no existing closed circle loop anywhere in the universe. It's pure theory. Without evidence for the existence of a closed circle loop, there is no way to recreate it. A philosopher at Chapman University in California, Emily Adlam, says, "Even if we had much greater technological powers than we currently do, it seems unlikely that we would be able to create closed time-like curves on purpose." In 1991, a physicist named Richard Gott put forward the theory that such a closed circle loop would be possible if there were two cosmic strings that moved past each other in opposite directions. Which is great. If cosmic strings existed, these strings are still hypothetical, being thought to have formed the very early universe by some theories. Another phenomenon that's seemingly allowed by relativity is wormholes. Theoretically, it's possible for space-time to be folded like a piece of paper, allowing a tunnel to be punched through to create a shortcut between two widely separated points, aka a wormhole. Again, the problem with wormholes is that although it's been shown in theory that they could exist, as a mathematical possibility, whether they exist physically is a different matter altogether. If wormholes did exist, they wouldn't have a very long lifespan. In fact, if they are two black holes that have joined together as is theorized, their intense gravitational field would collapse under its own gravity. There's more bad news for aspiring time travelers. These wormholes would be microscopically tiny, too small for a bacterium, let alone for a person to pass through. In order to solve the size and gravity problems, a large amount of negative energy would be required inside the atom. The energy of the atom field must have more positive energy overall, however, so even if tiny pockets of negative energy expanded inside, it's not a very realistic proposal. While relativity describes the behavior of large objects like humans and galaxies, quantum mechanics explains the very small, smaller than atoms, i.e. electrons and photons. Strange observations have emerged from quantum mechanics, notably non-locality. This is where a change in a particle's state in one location can instantaneously influence another, entangled, particle somewhere else. Einstein called this spooky action at a distance. It's been shown experimentally many times, but many physicists are unhappy with the possibility of non-locality. This is because in order for the effect to be instantaneous, the information would have to move faster than the speed of light. This is supposed to be impossible. In response, some physicists have come up with an alternative way to interpret the experiments. Some propose that when something looks instantaneous, it has actually traveled to the future and back again. This introduces retrocausality, i.e. events that take place in the future having an effect on the past. If this is the case, our linear concept of time isn't necessarily correct. In fact, it means information from the future is always spiraling back to influence the past. It's worth bearing in mind that this theory is not universally accepted either, with some seeing it as more outrageous than non-locality. In conclusion, we don't have a complete answer. Relativity and quantum physics aren't compatible with one another, but they work to explain certain aspects of our universe. Perhaps there is an overarching, unifying theory that links them, but it hasn't been discovered yet. For now, time travel remains out of reach, just like the more mysterious workings of the universe. Thanks for watching. Don't forget to subscribe.